Um, Primarily our sensor-based data in Luquillo. We're also using it to as a platform for doing data analysis and visualization on a project in New Hampshire with the Piscataqua Regional Estuary Program, which I'll also briefly mention. So we're going to do this talk in 4 parts. We're going to explore the CZ Manager software, talk a little bit about Observation Data Model 2, ODM2. We'll talk about the CZ Manager data lifecycle, and then we'll talk about WaterML, how that integrates with data.kuasi.org, and at least for our site, how I think it meets the needs for at least Luquillo for the HIMET project we talked about last week. Yeah, so CZ Manager was originally developed through the Critical Zone Observatory program, the NSF-funded program, and was developed as tools for Observation Data Model 2, and is really meant for and has been used to manage field observations with highly instrumented sites across Luquillo. So examples of the sorts of field observations that can be managed with the software are an LTER site, an experimental watershed, or an instrumented field site with or without sample-based observations. And in our Luquillo LTER database, we currently have over 45 million time series values from roughly 250 instruments that have been deployed at some point between 1983 and today. So the CZ Manager infrastructure looks like this. Data come into the ODM2 database. So ODM2 is a data model. So it doesn't imply necessarily a physical implementation, but in our case, we've implemented it as a PostgreSQL database, and data come into the system through logger networked data loggers, as well as uploaded data logger files. And those data are then processed with Bash and Python scripts to load the ODM2 database. Then we have a web front end, which is a Django Python website with maps using leaflet and graphing capabilities using high charts. We have WaterOneFlow Web Services, which we'll talk about, which link the database to data.kuasi.org. And you can do things like run Jupyter notebooks on Google Colab, or the Kuasi also has a Jupyter hub that I've run code on using an ODM2 Python API. And a number of these tools were developed through this CZO program with the larger team. But I've continued to use these tools, whereas most other groups never really successfully use them. We can also deploy export data as SQLite databases, which can then be uploaded to some data repositories such as HydroShare or the EDI data repository. So then just kind of a look at a map of the Alverde area in Luquillo, Puerto Rico. We've got a variety of different types of locations that we sample at, including weather stations, groundwater wells, stream gauges, soil, instrumented hill slopes, and soil pits with sample-based data, as well as others. From the map, you can click on one of the little balloons and that'll bring up a pop-up where then you can view all of the data that are associated with that particular site. And you can click on a link and view a plot of the data. And those plots again are done with high charts. And just within the Luquillo LTER database, we've also added in some USGS data, particularly at sites where we have other instruments, but there's a USGS gauge. We've added in the USGS discharge and stage height data, so you can plot those all together in the application. And we also have added in some neon data for cross comparison as well. And we've developed some other tools for cross comparing data across multiple sites. For instance, here we have a form with some type ahead fields. This is actually from our New Hampshire database, where you can see, I've typed in TURB and I'm going to select turbidity as a second variable. I'm going to plot for these two sites, the Upper Little Bay and the Great Bay in New Hampshire. And then we can see what the result of that is. We've got the Upper Little Bay, which is further up the estuary and is closer to the ocean, and it has more tidal influence. We can see that there's a stronger signal in the temperature from the pulses of the tides. And then we're looking at turbidity. And turbidity, we can see that there was a storm on May 5th, and the Great Bay in green, we can see there's more turbidity of a turbidity pulse from the freshwater influx from rivers that flow into the Great Bay versus the Upper Little Bay, which is again more tidally controlled system. So just showing like kind of how you can plot data of multiple sites and look at how they compare. Okay, now we go on to the second section of this talk, where we'll talk a little bit more about Observation Data Model 2. And Observation Data Model 2 was another NSF-funded initiative to expand on ODM 1.1 for different types of observations, to make it possible to make more spatially explicit different setups of sites with different types of instrumentation, whether we'll go through some examples. But yeah, there's multiple different physical implementations you could have. And we, like, for instance, we've used some SQLite databases as well as PostgreSQL. So like in ODM 1.1, it's most likely that you might have a monitoring site that is a single point location, but really you have multiple, your stream gauge is located and is sampling from a different location than a nearby weather station or a nearby groundwater observation well. And it might be different from the location where you take specimens of water to do water quality analysis on. And so these are just some of the information you can store and represent within ODM2. You've got a specimen that's taken at a particular time and place, but with a number of different measured variables on that specimen. And that specimen is really a unique thing that can be represented explicitly within the data model. Time series, that's pretty similar to ODM 1.1. And you could do things like do transects, where you have a sampling regime you're going to implement, where you're taking samples along a transect in a river. And these are just some examples. There's a number of other different things, like you could represent taking samples in XYZ space from a boat at different depths, and moving your boat around as whatever way you want. And you'd have all that, you could store all that information in the database. Now we're going to proceed on to the data life cycle of data in CZ Manager. So the data life cycle is the following. You generate metadata about your data, and you can add it into the ODM2 database using the CZ Manager web front end. Those are just web forms. You can complete lots of metadata about your data. You can, once you have your metadata specified about, say, a data logger file, you can upload the data logger file, validate the data. So that'll check that to make sure that the metadata and the data logger file match up, that all the columns in the data logger file match up with the metadata you've specified. And then it'll also check that the data aren't already in the database. And then you can process your data, which will ingest it into the database. Then following that, you can do QA/QC on the data. And once you've done QA/QC on the data will become available via WaterOneFlow Web Services and can be ingested into data.kawasi.org. Alternatively, we can also export data as an SQLite database for upload into another data repository. And so then to go into a little more detail about each one of those steps, to generate metadata, we just use this Django web app that I've developed. I did develop it with a little bit of help from a Critical Zone Observatory data team that was working for a while on this suite of tools. But I mean, mostly, 90% of this application I developed, really. But you can do things like set up the site where you're sampling, information about methods and actions. So like you might have a method for deploying a particular instrument, and then your action is actually deploying that instrument. And then you have like the variable you're actually recording with the instrument. And these are just some examples of some of the web forms. Then once you have all your metadata set up, you can upload a data logger file. So simply just you upload a CSV file, give it a name. You also have to specify each one of the columns from the data logger file that you want to ingest into the database and link it to the metadata you specified. And then some other things you can do with data that you're uploading. You can specify bounds checking. So you can specify like physical limits of what is a reasonable value for a particular type of value you're collecting with an instrument. And those bounds can either be hard limits or soft limits. So if there are soft limits, it's just going to add an annotation saying that the bounds have been exceeded. Or if it's a hard limit, it's going to set the value to null or not a number, but then it'll also record the original value with an annotation in the database. So it can still be backed out later. You can also do things like derive the physical thing you're trying to observe from raw data, like converting a millivolts into conductivity or some other thing. And you can do things like specify a stage discharge relationship and put it in an equation to convert a stage height measurement into discharge. And that can all be done via the web app as well. And there's different web app forms, just like I showed before, or like this one, to specify all that information as well. So after you've specified all that stuff, you're going to process a data logger file. And what that's going to do is it's going to allow you to validate your data to make sure that everything looks correct, the columns match, and it'll check to see if any of the data are already in the database. And if everything looks good, then you can go ahead and process the data and ingest it. And this, in some cases where we have networked data loggers, I'll have scripts running on the server that will basically automatically run this process. And then we also, after you've ingested the data, then you can also do QA/QC on the data via a QA/QC tool, which this animated GIF is showing you here. So this particular sensor has is recording values in sort of two different ranges. So here we're trusting the range with more values in it and saying these other values are not good. And we can set the data quality code to bad and add some annotation about what the issue with the data are. And we also set the values to not a number so that they will no longer appear in the plot. If you download the data, it'll still include the data value, but it'll be not a number. But then the annotation will also be exported with the data, and that annotation contains the original value as well. Then you can also do offsets and drift corrections. So you can, if you have two different time series or two different data logger files that are offset a little bit, you can just add an offset value to bring the time series together. Or you can alternatively, like if you had a time series that is declining over time due to sensor fouling or something, you could apply a drift correction that would, bring the values back into line with the sensor after you've serviced it to correct the drift. Okay, then once you've done the data QA/QC, the data will be available via WaterOneFlow Web Services. And that's done with a tool called WaFPy, which is an implementation of WaterOneFlow Web Services that includes ODM2. And so it's basically has a mapping from ODM2 to WaterML 1.1, which is similar to the ODM 1.1 sort of format. So then it can be, it's directly comparable and has that same format. And that project was originally developed by Emilio Mayorga, University of Washington. I'm currently using my own fork because I've kind of had to make some alterations to fit with the way we've implemented our data in our particular database. But that's also available on GitHub. Then, we can take a look at what the WaterOneFlow Web Services look like. And here, we're just showing a web front end for our REST services. that will serve the WaterML data. And we have some like samples sort of queries that you can run to see what the WaterOneFlow data look like. Okay, and so that is an overview of the data lifecycle in CZ Manager. We looked at how we generate metadata with web forms via the CZ Manager web app, how we can upload a data logger file and relate it to our metadata, how you can validate and process data, then use our QA/QC tool to QA/QC your data, and which will then make it available via WaterOneFlow Web Services. So we'll talk a little bit more about WaterOneFlow Web Services and integration with data.kuwasi.org. So before we looked at this REST service request examples, so like for instance, if you click on Get Sites, you're gonna see the XML to the right, which is the WaterML format for sites. It's specifying the Rio Itacos site, and that we're looking at luminous flux at this site in the air. Some of this metadata is not completely complete, but that may be an issue I need to address a little bit more. And so with these WaterOneFlow Web Services, I can register this with HIS Central. So we've registered this web service here, and we can use this test page to make sure that HIS Central can read our web services and retrieve the data. So here, we're just like getting information about the sites, and then we're going to get information about the specific site. Then it's going to show you the different variables that are available at this site. And then you can pull through some values. And this is an example of how you can test, how we test that the web service is properly connected to Kuwasi's HIS Central. And then once that's all working, then we can pull the data across to data.kuwasi.org. And in there right now, if you go to Luquillo in Puerto Rico, you can see there's a good deal of data that have been ingested into the system there, including climate, soil moisture, soil O2, and water quality data, as well as some met data. And then, from there, you can select time series and save it as a CSV, export it. So I'm assuming that should be what we need for HiMet. I don't know if the plan for HiMet is to actually get data into data.kuwasi.org, but our data is already in there and we can export it as CSV files. That is pretty much everything. So we explored the CZ Manager software, looked at observation data model 2, looked at the CZ Manager data lifecycle, and web services, WaterOneFlow Web Services, and integration with data.kuwasi.org. The application is on GitHub. You can go to this GitHub page and download the application. We have documentation about the application on GitHub.io at this link. I can also make these slides available to people. There's more information about ODM2 on GitHub, and you can also contact me with any questions. Our Luquillo application is behind a username and password, because we have raw data in there that's has not been QA QC'd. But for the PrEP New Hampshire data, those data are already QA QC'd, and we've just taken data from New Hampshire Department of Environmental Services and loaded it into a database for that particular project. So since that data is all supposed to be publicly available and has been QA QC'd, that particular copy is available to the public. We also have a sandbox implementation of the application, which you can learn about on our GitHub.io page. And if you want access to that, you want to poke around some more, again, just contact me and we can talk about it. I can get you in there. Yeah, and that's it. Can open it up for questions.